This is the last part of Lab 6. We're going to look at some miscellaneous circuits. Some are going to be inverting, others non-inverting configuration. Let's start with a pretty simple circuit. This circuit has a current input rather than a voltage input. We ask to analyze any circuit. We're going to say, is there negative feedback? And sure there is. The output is connected to the negative input through a resistor, so there's no question there's negative feedback. So that means that the op-amp tries to keep the negative input at the same voltage as the positive input. So V equals 0 volts. It's virtual ground. And V out is going to be a function of I in. No current flows into the op-amp. Which means that the current that flows through RF has to also be I in. But the current that flows through RF, IF, is equal to V minus V out over RF. V minus is 0 volts minus V out over RF, or IF is equal to minus V out over RF. But we also know that the current that flows through the feedback resistor is also equal to I in. And that means that V out is equal to minus I in times RF. So this circuit takes an input current and turns it into an output voltage. This is a current to voltage converter, and it's inverting. If you consider positive input current causes a negative output voltage. It's a useful circuit anytime you have some sort of source or sensor that's putting out a current. Currents are hard to measure, voltages are easy to measure, so we like to convert currents to voltage. We can obviously use a resistor. So what is the advantage of this circuit over this circuit? Well, the circuit has the advantage that V out is positive, if I in is positive, but it has the disadvantage that its input impedance is RF, whereas the input impedance over here is 0. Why do we say that? Well, the input is looking directly into ground. Now, voltage sources like very high input impedance, but current sources like very low input impedance. So this has the lowest input impedance we can get, 0. That's definitely a benefit. Also, as I in flows in here, the voltage across RF increases, which means that the voltage across the current source changes. Now, theoretically, a perfect current source doesn't care what the voltage across it is, but the real world, current sources tend to be somewhat voltage sensitive. Here, the input that the current source sees is 0 volts. It's virtual ground no matter what current flows. So the voltage across the current source stays the same, and it offers better linearity. We get a better current source when the voltage across the current source doesn't change. So in the same way that our differentiator and integrator were improved by using a op-amp, our current to voltage converter is improved by using an op-amp. This is a nice circuit. Let's think about where we might want to use this. Well, it turns out we have a whole class of sensors that output current. Most of our photo devices that are sensitive to light, are current devices. For example, if we take a diode and we expose it to light, current flows in the reverse direction. So if we bias this, it's a photodiode. When light hits it, current flows in the reverse direction. We can convert that to a voltage with a current to voltage converter. And it has all the benefits that we like in a current to voltage converter. This voltage is always 0 volts. So the voltage across our device is 15 volts, and it doesn't change when current flows through it. That makes it a better current source. This current source has very high output impedance. That's the definition of a current source, and it's looking into a very low impedance. So there's no effect on the current source by the input impedance of the circuit. The circuit is connected to ground. So this is a light detector. V out is equal to 0 in the dark, and it's less than 0 when there's light. We can't get a positive voltage out of here because it would require current to flow in this direction, which isn't going to happen. Current isn't going to flow from 0 volts to 15 volts. Okay, you're going to build this in lab and see that it works. I should point out that we also have, this is a photodiode. We also have phototransistors. The main difference is that the phototransistor generates current in a BJT base, and that's multiplied by beta to cause more current to flow in the collector emitter circuit. So a phototransistor is somewhat more sensitive than a photodiode. I'm not quite sure if we have both in the lab. I certainly know. Actually, I think we do have both photodiodes and phototransistors. And we'll be using them anytime we need to detect light. Phototransistors and photodiodes can be sensitive to a particular wavelength. You might have an infrared receiver photodiode. You might have one that's in the visible range. You can always look up the specs to see what they do. So let's take a look at another circuit. Some non-inverting circuit. What's interesting about the circuit is we stick the load between the output of the op-amp and the negative input. Well, this circuit looks suspiciously like our non-inverting amplifier with gain, and it is. And what's different is how we think about it. Since there is negative feedback, this point is at Vn. That means that this resistor has Vin over it. It means that the current that flows through here is Vn over 100. But our op-amp rules say no current flows in here, which means that this current has to come through here. So the current through the load is Vn over 100. Doesn't make a difference what RL is within limits. RL could be a short circuit. We'd still have Vn over 100. Could be 100 ohms. Could probably be 1K. Sort of depends. We'll talk about what it depends on just a second. So this is a constant current source. The current through the load is totally dependent upon Vn and the value of this resistor. In fact, this resistance could change dynamically, and the current through it would remain constant. We are limited by a couple things. We can usually only get about 20 milliamps out of an op-amp, so we can't get more than 10 or 20 milliamps through the current source. Also, this voltage can't go above VCC or VEE, below VEE, so that's going to limit the maximum RL, depending on the current. For example, if we have 1 milliamp through here, so 0.1 volt here, and we have VCC here, well, 0.1 volt is 1 milliamp. We can only have about, if this is 15 volts, it's approximately 15 volts across here. 1 milliamp through 15 volts is 15K. So this has to be relatively small. But for small currents and relatively small loads, this is a pretty good constant current source. It has one big advantage, which is it is voltage controlled. We can vary the current just by varying Vn. And in fact, we can switch the direction of the current. If Vn is positive, this voltage is positive, and current flows through the load like this. If Vn is negative, this voltage has to be negative, and current flows in the opposite direction. So this is a bidirectional voltage-controlled current source. Notice we really don't care much about what the output of voltage of the op-amp is, as long as it doesn't exceed the power supply limits. All we really care about is this current. So another nice circuit. Now, suppose we needed more than 20 milliamps out of the through our load. Well, then we resort to adding a BJT to our circuit because our BJT could give us beta more current. If we have 2N3904, we could get up to 200 milliamps through it because that's the maximum current through the 2N3904. If we used a power transistor, we could get multiple amps. So we can modify this circuit with a BJT. One other issue about this circuit is notice that neither end of RL is connected to ground. This is known as a floating load. That's fine. There are some loads that require that one end be connected to ground, and you'll see that the transistor, the BJT version of this current source, has a grounded load. You'll build both this version and the grounded load BJT version in the lab. One more circuit. Suppose we wanted to drive a loudspeaker. Loudspeakers are inductive loads. They're 8 ohms typically. We have a source of some sort. We want to buffer that source. So maybe we add ourselves a op-amp buffer. Now, we can't drive an 8 ohm speaker directly from a op-amp because we only have 10 or 20 milliamps, and that's an incredibly small amount of power. Nobody's going to be very happy at your party if they have to stick their ear against the speaker. But that's okay. We know how to convert a small current into a bigger current. We can use a pair of transistors. In a push-pull configuration. So now the op-amp drives our push-pull, and if we need to put current into the speaker, we turn on the 2N3055. And if we need to pull current out to the minus supply, we turn on the 2N2955. And now we can get several amps into the speaker. We get lots of nice loud sound. The only problem is this transistor is only on when this input is above 0.6 volts, and this transistor is only on when this input is below 6 volts. So if we put in a sine wave, what we're going to get out is a distorted signal. There's going to be a period where the output is 0 when this input is less than plus 0.6 but greater than minus 0.6, because that's not enough to turn on this transistor or this transistor. And I can tell you that this sounds pretty horrible. Also, if we're connected to a music passage and the music passage is very soft, the music passage may never exceed plus 0.6 or minus 0.6. We're not going to hear it at all. So we need to fix this, and as a colleague of mine once said, feedback fixes everything. So let's cut the feedback path, and instead of taking our feedback from the output of the op-amp, let's take our feedback from the loudspeaker. Well, do we still have negative feedback? If the output of the op-amp goes positive, this point goes positive. It's 0.6 volts less, but it still increases when the op-amp output increases. That means the minus input increases, and that's our definition of negative feedback. So we have negative feedback. If we have negative feedback, V source and V minus should be the same. If that's true, then the voltage across the loudspeaker is V source. That's exactly what we want. We've gotten rid of the distortion. And in fact, what we'll see is the output and the input are the same. Now, how is that possible? Well, it's possible because the op-amp is undoing the crossover distortion. If we look at the voltage out of the op-amp, what we're going to see is it follows the input, jumps. This is 0.6 volts. This is minus 0.6 volts. Jumps down to minus 0.6 volts, follows the input. So what the op-amp is going to do is it's going to quickly transition from plus 0.6. When it's at plus 0.6, this transistor is just barely on. It's going to jump down to minus 0.6, which will turn on the PNP, and then it'll follow the input. So we've got this dead zone that we're jumping through and getting rid of the crossover distortion. This is, by the way, what we talk about when we're hiding the dog. And in fact, I can draw this in a way that maybe makes that a little clearer. And you'll see why this is actually somewhat of an odd circuit. Here's the output of the op amp. Doing a very bad job of this. Because it's a very strange way to draw it. But now we can see that we're not taking our output of the circuit from the output of the op amp, but we're actually taking it from the minus input of the op amp. So this is the feedback function. I should put it all on the screen. So this is f of v. This is f inverse of v. And what we care about is having the op amp undo f of v. F of v is our crossover distortion. We don't want that. But by putting it in the feedback loop, the op amp undoes it. And the result is if we put a nice sine wave here, we get a nice sine wave here because there's negative feedback and the op amp can undo that. You're going to build this in the lab, and if you're interested, I've included a video showing a demonstration of this. So there's 3 different circuits using op amps to do things that we wouldn't know how to do otherwise. You're going to go into the lab. Let's take a look at what we're doing next. You're going to take quiz 4, which asks you a bit about how this all works. And then you're going to build 3 circuits. You're going to do the push-pull buffer and show how feedback fixes the crossover distortion. You're going to build a current to voltage converter, and you're going to build a current source. And we have 2 types of current sources, one which uses the floating load and one that allows you to use a grounded load. And when you're done, we'll come back, we'll go over the quiz discussion, and then we'll be done with lesson 6.